So in chapter 4 there are a couple of sections left we have still to discuss. Now the section we want to discuss today is section 4.5, which is called Summary of Curve Sketching. Now, I'm not sure whether you learned this here in Taiwan in high school, but maybe you have seen some examples like this already in high school. So our main aim is we have given a function, we have given the expression of a function. For instance, you find in our textbook the function f of x is equal to 8x to the cube minus 21. X squared plus 18x plus 2. So for instance, you have given this function here. The main task is to figure out, okay, how does the graph of the function looks like without the graphing device. Now, I should maybe say, also in our textbook, you see you have at the beginning a short discussion which explains you why we want to do this, so why we want to use calculus in order to figure out how such a function looks like. Because actually nowadays you have very good programs like Maple, where you can just plug in this function and Maple can give you in a few seconds the graph of the function. Okay, so why is it necessary to use calculus in order to discuss some essential properties of such functions? Now, in our textbook you see a couple of reasons. So if you do not have a graphing device like Maple, you can just, the only method you have in order to draw the graph is you compute some points. So you choose some x, compute some points, you plot what you get, and then you try to figure out, okay, how does the function look like? But of course, you cannot be certain if you have 2 points, okay, how to connect them. Normally, what you will do is more or less linear, but of course, you will never be sure what happens between them. That's the first thing. So this is if you just have a calculator. But if you use Maple, then you can actually get the whole plot. Now, also for Maple, the problem is that you still have a problem, namely how to choose the range of x, because you have to tell Maple, okay, plot this function over a certain range. Now, the range which you are going to choose for x normally depends on okay, where do you expect that this function has the essential properties, okay, the important properties like local. If you roughly know where the local extremas are located, where the inflection points are located, then you know how to choose x. Okay, otherwise you just can try around. Of course, you can plot it first over a certain range of x, and then if you think from the result you maybe cannot see all the properties, the essential properties of the function, you can choose another range for x and plot it once more and so on. But still, there might be it might be possible that you that like this you can never capture, okay, the essential properties you want to know about this function. Now, this function is a good example because in our textbook you see the plot of this function. If you choose the range of x very carelessly, okay, this function roughly looks like. So you can find this in our textbook. I think it looks something like this here. If you choose, if you plot x over a certain range, you see this plot in our in our textbook, and because you see that the behavior of this function, okay, essentially should be something like x to the cube, okay, you could try to believe, okay, this essentially looks like the function x to the cube. But if you zoom in, then you will indeed recognize that you have a local maxima and a local minima at this point here. So here I plot the same function, but over a smaller window concerning x. And what I get is, okay, if I just look at this, I might be convinced that, okay, 0 is inflection point, and the function is increasing everywhere. Okay, but if I zoom in, okay, I see that this is not true. Okay, and of course, this is a simple example, but even if you just rely on a graphing device, you normally do not know how to choose the range for x. And you can just try around in order to find the essential properties of a function. Okay, so now what we want to do, our aim in this section is to use calculus in order to completely, in order to find out how this function looks like, in order to capture all the essential properties of this function. And the way you do this in practice is normally you use both Maple and the tools we are going to use here in this section, because Maple then helps you to get you a clearer picture of the function, but you can use calculus in order to decide, okay, over which range of x, for which x you have to plot the function in order to capture all the essential properties of the function. Okay, so actually all the tools we have, we need in order to discuss the graph of such a function we have already developed, so we just have to collect them in this section. And you see that in this section you have a rough guideline how to do such a analysis. So how to by using calculus, how to figure out how the graph of this function looks like. So you see in our textbook, the first thing is you should try to figure out what is the domain of the function. So this is the first thing. Then the next thing is you should try to figure out the y and x intercepts, because then you know roughly where the function is located. Then the next thing you should discuss is symmetry, so whether the function is an even function, an odd function, or maybe has no symmetry properties, or is a periodic function. Because symmetry normally can help you quite a lot, because if you know that the function is symmetric, for instance, about the y-axis, this essentially means you just have to discuss the function for positive x, and for negative x, you get it for free just by reflecting about the y-axis. So maybe just to use the same order as in the textbook. The first thing is the domain. The second thing are x and y intercepts. Y-intercepts. Then the third thing is symmetry. So for symmetry, you have even, odd, or periodic functions like sine and cosine are periodic functions. So for instance, if you have a function which is periodic with a period, for instance, 2 pi, then you know you just have to discuss the function in the interval 0, 2 pi, and that's enough. And then you just shift it, and you know how the function looks like over all real numbers. So this is normally the third item. Then what we are going to discuss are asymptotes, so horizontal and vertical asymptotes. We have already seen that that in order to figure out whether a function has asymptote at some points, essentially what we have to do is compute limits. So normally here we will also use the rules. We will need the rules of the L'Hopital in order to compute the limits. We will see today except horizontal and vertical asymptotes. So except asymptotes, which are just lines, it's also possible that there are other types of asymptotic behavior, which means that, for instance, it's also possible that the function x, as x tends to plus infinity, is getting closer and closer to, for instance, the line y is equal to x, which is not either vertical or horizontal. And in this case, we talk about a slant asymptote. So such a asymptote is called a slant asymptote. We will see an example in a minute to illustrate this. Then after we have found those 4 properties, here I should maybe emphasize that this is something very important, because a graphing device can never capture the asymptotic behavior as x tends to plus or minus infinity. For this, you certainly need calculus, because you have to restrict the viewing rectangle in Maple, so it's not possible that you plot the graph over from minus infinity to infinity. So this is something where you indeed need calculus in order to figure it out. And then what we do next is we compute the first derivative, which then helps us to clarify the behavior of increasing, decreasing. Okay, and once we know the increasing, decreasing behavior of the function, we normally know everything about local extrema, which is the next point. Then we look into the second derivative and get information about the concavity behavior. And once we understand the concavity behavior, we, of course, can determine whether there are inflection points or not. Okay, and then the last item is actually the reason why we do all this is to plot the graph. So using this easy scheme, you can plot the graph of a function without using a graphing device, okay? Because these are the essential properties, and once you have gathered all those properties, it will be easy to plot the graph of the function. Now, the important thing, if you do something like this, if you do examples like this, because you see in our textbook there are many examples, the important thing is that you, so you do not necessarily have to stick to the same order as the author, but you should do this in a systematic way. So you should, every time you should use the same order that you don't forget some of the essential properties. So maybe if you do examples like this, try to cover all those points which are covered here in this section of the textbook, but you can choose your own order. Of course, from here, starting from here, of course, it's not possible to choose your own order because you will need first the first derivative. The first derivative tells you something about increasing, decreasing, and already once you know this, you know this here, and then you compute the second derivative. And once you know this, you can locate the inflection points. So, for instance, for local extrema, we have seen there is also a second derivative test. But if our aim is to get all those information to figure out how the graph of a function looks like, okay, normally you do not have to use the second derivative test, okay, because from this information, normally you know already everything about local extrema. So you can use the first derivative test, and that's it. Okay, so maybe let's do an example. Okay, so for instance, this polynomial. Okay, and let's just work off the same points. So we start with the first one. The domain is easy. The domain is here the set of all real numbers. So this is easy. Second thing is x and y intercepts. Now the y-intercept is f of 0 is equal to 1. So at x is equal to 0, we are at 1. And for the x-intercepts, we have to solve this here. Okay, but it's not so easy for this equation, so we do not do it. Because for this, we essentially need a program like Maple to do this, or some numerical method, which we will also learn in the next section. So if it's not possible to find the x-intercepts, we just forget about it. Okay, it's not so essential in order to figure out how the graph looks like. We will get information about this equation once we have gathered all the information about the increasing behavior, decreasing behavior, and so on. Normally, naturally, we will also be able to figure out roughly where the zeros are located. Okay, so we are not able to do this, so we don't do this. Now, the next thing was to find symmetry. So you see no symmetry. Okay, so this was easy. Now, of course, there are no vertical asymptotes, and there are also no horizontal asymptotes, because you see that the limit of f of x as x tends to infinity is equal to infinity, and the limit of f of x as x tends to minus infinity is equal to minus infinity. Okay, so there are no asymptotes. Okay. Now we look into the derivative. So the first derivative, 10x to the 4 minus 10x Okay, so we can write this as 10x x to the cube minus 1. But this we can write as 10x x minus 1 x squared plus x plus 1. Okay, so we see that there are two critical points, 0 and 1. Okay, so critical points. Zero and 1. Okay, and we see that if x is smaller than 0, okay, so in this case, this one is negative, this one is negative, but this one here is always positive for all x. So we see that in this case, the derivative is larger than 0. So this means increasing. Okay, then we have x is between 0 and 1. In this situation, this one is positive, this one is negative. So we have the derivative smaller than 0. So we have decreasing. And if x is finally larger than 1, then we see that the derivative larger than 0. So in this case, increasing again. Okay, we also see, because these are the only critical points, and we see that the monotonic behavior will change at both points. So at 0, we go from increasing to decreasing. So here we have 0 will be a local maximum, and 1 will be a local minimum. Okay, so this was now already A, B, C, D, E, F. Okay, so this is E here. Okay, so x is equal to 0 is a local maximum, and x is equal to 1 is a local minimum. Okay, now we have to look at the second derivative. Okay, so we have to take the derivative here. So the second derivative is equal to 40 x to the cube minus 10. Okay, so, and we have to equate this equal to 0. So we see that here we get one solution, 1 over the third root of 1 over 4. Okay, we also see that if we want to discuss the sign of the second derivative, so what we have is we can write this as 10, then we have 4x to the cube minus 1. So this is essentially what we have. So we have here you see from this expression, you see already if our x is larger than this one, okay, this will be larger than 0. And if our x is smaller than this one, this will be smaller than 0. Okay, so we have that this is now for the concavity behavior. So if x is smaller than the third root of 1 over 4, then we have, because this will be smaller than 0, so the second derivative will be smaller than 0. So we have concave downward. And if x is larger than the third root of 1 over 4, then you see that the second derivative will be larger than 0. So we have concave upward. Okay, so the function will change its concavity behavior at the point x is equal to the third root of 1 over 4, so this must be an inflection point. Okay, so the third root of 1 over 4 is an inflection point. Okay, and this information should be normally enough to plot the graph. Okay, now we gather everything and plot the graph. Okay, so now actually most of the things are already erased. If we are, maybe let's look at the function. Let's at least write the function once more onto the blackboard because I don't remember it. 2x to the 5 minus 5x squared plus 1. Okay, so we saw at x is equal to 0, the function is equal to 1. So if this here is 1, we saw that the function is increasing, okay, to the left and reaches here a local maximum. Then at x is equal to 1. Okay, so if you plug in, you see the function is equal to minus 2. Okay, so you are here. So from here to here, we know that the function is decreasing and then increasing again. So here we have a local maximum value. Here we have a local minimum value. As x tends to minus infinity, the function tends to minus infinity. As x tends to plus infinity, it tends to plus infinity. And we see that at this point here, and this point is somewhere between 0 and 1. It doesn't matter. So this point is somewhere in between. Here we have a point of intersection, and to the left of this point here, the function is always concave downward, and it's becoming concave upward than here. So from this information, we can essentially figure out how the function looks like. So we will have something like concave downward. So we will have something like this here. Then it remains concave downward. And then from some point on, we'll get concave upward, and then and then the function tends to plus infinity. Okay, and so now the point here, the point of inflection, is roughly here. Okay, so this here is the inflection point. Okay, so this is the way we do such a curve sketching, such an exercise. Okay, such a discussion. So we gather all the information and we use all the information in order to plot the graph. You see here, this can be helpful in order to figure out, because we had here a polynomial of order 5. Okay, and if you want to know, okay, how many zeros does such a polynomial have? Okay. This can be helpful in exactly locating the number of zeros, because now you know, okay, it's only possible that this polynomial can only have three real zeros. Okay, because this we know from the information of the graph. Okay, so sometimes if you have to figure out, okay, how many zeros does a polynomial have, this is one way to do it. Discuss the graph of a function. Okay, so maybe let's look at one more example. Okay, so it's the same aim. How does the graph of this function looks like here? And we want to figure this out without having a graphing device. Now, the first thing is the domain. Now, the domain for this function is easy as well. This function obviously is defined for all real numbers. The second step, okay, x and y intercepts. You see the y-intercept is equal to 0. And for the x-intercept, you have to solve x minus 3, x to the 1 over cube is equal to 0. Okay, so this is an easy equation. So you see that x to the cube is equal to 27x. So you have x times x squared minus 27 is equal to 0. So you get 3 solutions. X is equal to 0. x is equal to plus minus square root of 27. Okay, so we have now found the x and y intercepts. In particular, we see that we have three intersections of this function with the x-axis. Now, symmetry. So how about symmetry? You see that f of minus 1, minus x, okay, if you plug in minus x, you can take out the minus x, is minus f of x. So this is already helpful. So this is an odd function. Now, asymptotes, there are no asymptotes, so no asymptotes. Okay, so you see, but you see that the limit, even so, if there are no asymptotes, it sometimes pays off to compute the limits. So the limit as x tends to infinity is equal to infinity, and the limit as x tends to minus infinity is equal to minus infinity. So essentially, this term here is the dominating one. Of course, if you compute this limit here, what you, strictly speaking, you would get infinity minus infinity. So you have to use the rules of the L'Hopital. It's not necessary here because we know that this function must grow much slower than this one. So this function will outperform this function here. So you certainly get here infinity. Okay, now we go on to compute the first derivative. Okay, so let's compute the first derivative. So this is 1 minus x to the minus 2 over 3. Okay, so you can write this as x to the 2 over 3 minus 1 over x to the 2 over 3. Okay, so the critical numbers okay, you have plus minus 1, okay, from here, and you see that at 0, x is equal to 0. The derivative is not defined. Okay, so we know that local extrema, okay, can just occur at critical numbers. Okay, so all the extrema can just occur here. I remember last time in the in-class homework we had an example similar to this one. Okay, and I remember, and quite a lot of students forgot that 0 is that all the that you have, that is not enough to compute the derivative and equate it to 0 in order to find the critical numbers. But you have also to include the numbers where the derivative does not exist. Okay, and indeed, in the example in the in-class homework, I think the local maximum, the absolute maximum, was taken on at the critical number, not at the critical number where the derivative does not exist. Okay, so you have to be careful here. So here you have 3 critical numbers. Now, but actually, here we are still discussing increasing and decreasing behavior. But you see here, if the absolute value of x is larger than 1, then you see that the derivative, okay, must be larger than 0. Okay, so here you have increasing. And if the absolute value is smaller than 1, okay, then the derivative is smaller than 0. So you have decreasing. Okay, now we can discuss the critical, whether at the critical points we have local extrema or not. So you see here that at the points plus and minus 1, okay, the behavior concerning the monotonic behavior of the function is changing. Okay, at minus 1 it changes from increasing to decreasing, and the plus 1 from decreasing to increasing. Okay, but 0 nothing. Okay, so 0 is the only critical number which is not a local extrema, but those plus minus 1 are local extremas. So plus 1 is a local minimum, and minus 1 is a local maximum. Okay, now we have to compute the second derivative. Okay, so the second derivative is equal to 2 over 3 x to the minus 5 over 3. Okay, so we see that the second derivative, because here the power is odd, where here the power is even. So if x is larger than 0, then this will be smaller than 0. If x is smaller than 0, this will be smaller than 0 as well. And if x is larger than 0, this will be larger than 0. So we have at x is equal to 0. Okay, so here we have concave upward, and if x is larger than 0, then the second derivative, downward, and here we have concave upward. Okay, and we see that at x is equal to 0, we have an inflection point. Okay, so this is maybe also interesting, okay, that at x is equal to 0, we have an inflection point, because you see the second derivative is not equal to 0 at x is equal to 0, it does not exist. Also for inflection points, you have to include the points where the second derivative either does not exist or is equal to 0. Okay, so you have something similar to the critical numbers, okay, but related to inflection points, the points where the second derivative is either equal to 0 or does not exist. And at all those points, it might be possible that you have an inflection point. Now, this information, of course, is enough now to plot the graph. Okay, so what do we know? We know that as x tends to minus infinity, the function tends to minus infinity. As x tends to plus infinity, it tends to plus infinity. We know that minus 1 and 1 are two essential points. At minus 1, we have a local maximum. At plus 1, we have a local minimum. And we know that here the function is increasing, here the function is here the function is increasing, and here the function is decreasing. Okay, and we know that the function changes at x is equal to 0, the concavity behavior from being concave downward to concave upward. This essentially, as you see from this information, this will be enough in order to plot the graph. Okay, so you see, of course, you can also compute, for instance, at 1 and minus 1 the function values, because there you have local extremas. So the original function was x minus 3x to the 1 over 3. So if you have 1, then you have minus 2, and here you have 2 because of symmetry. Okay, and the behavior like this. Okay, so you see here's the inflection point, here's the local, not really. Okay, so here you have a local maximum, here you have a local minimum, here's the inflection point. And the behavior is changing from concave downward to being concave upward. And the function is increasing outside this interval and decreasing inside the interval. Okay, so the main aim of doing such a discussion, okay, of a function is to figure out the graph. And in the last step, you should be able to plot the graph, okay, via all the information you have gathered about the function. So any questions to this? Okay, so now essentially we do not need the calculator anymore, or the maple anymore, in order to plot graphs of functions. But of course, some functions might be very complicated, so it's maybe not feasible to get all those properties. For instance, it might be not possible, if you compute the derivative, it might be not possible to figure out where is the derivative 0, equal to 0, because this would essentially yield to, this would give an equation you cannot solve for properties like this. And you can say nothing about, even about local extremas, you can say nothing in this case. So sometimes, for some examples, you have to gather as much information as possible, and not it's not possible to gather all the information I have collected for the examples I just presented you, then you just have to to gather as much information as possible in order to roughly understand how a function looks like. Now, I told you already that sometimes we encounter asymptotes which are neither vertical lines nor horizontal lines, which are more complicated. Now, one example for this, for such a so-called slant asymptote is given in a textbook. So, for instance, if you have f of x is equal to x to the cube over x squared plus 1. So you see that if x tends to infinity, this function here will tend to infinity. If x tends to minus infinity, this function will tend to minus infinity. Okay, so this function does not have any asymptote, okay, any horizontal asymptote. Okay, but you see that you have learned in high school that you actually can divide this here by this one, so so-called long division. Okay, so maybe I do it once. Okay, so you can. Okay, so first is x times. Then you write here x to the cube plus 1. Okay, and then you subtract those. Then you have 1 here. So you can write this as x plus 1 over. Sorry. Okay, now it's correct. And now you are finished because the degree here is smaller than the degree of the divisor. So you have. You can write this as x minus, and then you have here x over x squared plus 1. Now the essential thing is that if you subtract here what you got here by the long division, okay, from the original function, so if you and take the limit as x tends to plus or minus infinity. Okay, so then you have, this is the limit, x tends to plus or minus infinity of minus x over x squared plus 1. Okay, but this is in both cases equal to 0. Okay, so this means that as x is getting very large or x is getting very small, this function behaves in the same way as this function, approaches this function. Okay, so here what you have is, of course, we have to discuss more properties of this function in order to figure out the complete behavior. But what we already know by now is that as x is getting very large or very small, the function will approach this function here. Okay, I think in your textbook you can see if you do the other. So, for instance, if you get more information about this function, if you work off the same scheme I have worked off before twice, okay, you will figure out that the function, if I remember correctly, looks something like this here. Right? I don't remember. Okay, so here you see the essential thing. We haven't discussed other properties. So you have here, this function has 3 points of inflection. Okay, so we haven't worked this out. If you compute the second derivative, you will find out that this function is always increasing. If you compute the second derivative, you will figure out that the function will change its concavity behavior 3 times, namely at this point, and at the point which is symmetric to here. Because this function is symmetric, so essentially you just have to discuss one part. So you have 3 points of inflection. So it will look like this here. But what is essential for us here is that you have a similar asymptotic behavior, but the function is not approaching a line as a function would do if we would encounter a vertical or horizontal asymptote. But the function is approaching, the function is of course approaching a line, but not a horizontal or vertical line, okay, as is the case for a vertical and horizontal asymptote, but approaching the line y is equal to x. Okay, and similar, for instance, this is quite helpful because it tells you already for x large, okay, it gives you already a feeling how this function here looks like. Okay, for instance, if you look at the let's say the hyperbolic or hyperbolic cosine of x okay, so here you see that as x is getting large, okay, this here will be very, very small. Okay, so as x is getting large, this function will behave like e to the x half. Okay, so e to the x half will be the you can say the asymptote of this function here. Of course, it's not a line here. Okay, so it's pretty different, but it has the same flavor as here. Okay, so if you choose this function and you subtract e to the x half and you take the limit as x tends to plus infinity, you will figure out, okay, that the limit is equal to 0. So as x is getting large, okay, this function behaves like e to the x half. And the same if x is getting slow, okay, so this if x is getting small, this one will be very small. So the function will behave like e to the minus x half. Okay, so if you plot those two graphs, okay, so if you plot e to the x half, so let's say it looks like this here, and you plot e to the minus x half, let's choose another color. Okay, so this point here is 1/2. Then you know as x is getting very large and x is getting very small, this function here, okay, will behave in the same way essentially as the function e to the x half and e to the minus x half. Okay, so this is already helpful because we know that the hyperbolic cosine looks like this here. So essentially it approaches those two functions. Okay, so you can say those two functions serve as asymptotes, okay, of the original function, and this is already quite helpful in order to understand how this function looks like as x is getting very large and very small. Okay, but if you have as you have seen before, if f of x is a rational function and the degree of the numerator is larger than the degree of the denominator, then you always can use long division in order to find, for this case, which I just showed you, the function f of x is equal to x to the cube over x squared plus 1. Okay, so for this example, here the degree of the numerator is the degree of the denominator plus 1. Okay, so if you do long division, you will get a polynomial of degree 1. Okay, as asymptote, so essentially a line. But of course, if you have here a polynomial, for instance, of degree 4, and you can do the same, you can also divide, and you will get a quadratic polynomial, and the function will, so this function will, as x tends to plus or minus infinity, will approach the quadratic polynomial. So you get something similar by long division. So long division is, you can always use it in order to figure out a function which has the same asymptotic behavior as our given function. Which means that if x is getting large or x is getting small, you get the same behavior. We will go on to section 4.7, which discusses another important application of the theory we have developed so far. In particular, section 4.7 discusses why we are interested in finding local extremas. Here you have seen already one application. The second application is so-called optimization problems, something which is obviously important in applications where you want to optimize things, like a company wants to optimize the profits, so make the profit as large as possible. Or if you travel, then you want to maybe minimize the travel time, so you do not want to spend too much time on traffic, but more time on sightseeing. Also, there are some basic principles in physics, as you might know already. One is called Fermat's principle, which tells you if light is traveling from one point to another, the path light is choosing normally is the path which minimizes the travel time, because the speed of light is constant. So this is called Fermat's principle, and according to this principle, to prove many of the basic laws of optics are nothing else but optimization problems. We will see an example for this in a few minutes. The next thing we want to do is solve optimization problems. So we have given some problem, and we have to optimize some quantity. Now, also for such problems, in our textbook you find the step-by-step program how to solve such problems. So maybe let's look at a specific problem in order to explain this. Assume we have 500 meter of fencing. What we want to do is we want to enclose a field against the pawn. Okay, now how do we choose the fencing? So we have two parallel lengths of fencing which are perpendicular to the wall of the barn. So two parallel lengths perpendicular to the wall. To the pawn, and joined by a convex semicircle. Semicircle. Opposite the pawn. Okay, what we want to do is we want to maximize the area of the field. So maximize. Okay, now I guess you have done similar examples in high school. I think I saw some of them in high school books. Now, in our textbook, it's roughly explained how to do such examples. The first thing, of course, is to understand the problem. The second thing is to, which is always helpful, which is most of the time helpful in such problems, is to draw a diagram. Or to plot, or to draw a picture. Okay, so here essentially you have a barn. So let's assume this is the wall of the barn, and we have two lengths which are parallel and perpendicular. So this means something like this here. Okay, and then this is joined by a convex semicircle which is opposite to the barn. So we have something like. Because this here is the barn, okay, so the fencing we will just need for this part here. Okay, so this is our field here. And this is what the yellow area you see here is what we want to maximize. Okay, so we see obviously that we have we can either make this here larger and larger, okay? Then at some point, we just have a semicircle, so we make this smaller, or we make this larger, but then we have to make this smaller and smaller because the length here of the fencing is restricted, okay? So as we make this here smaller, we have to make it the whole thing larger, okay? And the area, you get a certain area, and as you make those two lengths here smaller, okay, the semicircle will grow. Okay, so the question is, okay, how to choose here this length here, okay, in order that the area which is enclosed by the fencing is getting a maximum. The second step, so the first step is very often to draw a picture. The second step is to introduce notation. Okay, so we will call this here L, and we call this here W. Now, the next step is to write down the quantity which you want to maximize as a function of the other quantities. Okay, so here we are interested in the area. Okay, so the area is equal to L times W times, and then you have here the area of a circle. So you have plus. So this is the area we want to maximize. You see that the area still depends here on L and W, two functions. We will actually learn in the next semester how to solve such optimization problems. In terms of two functions is also possible. There is a theory for this, but this we will learn next semester. So because this semester we are mainly looking at functions in which just have one variable. Okay, so the next step is to eliminate all the variables such that A is just a function of one variable. And this will, in such optimization problems, this is easily done by this condition here, which you have. Okay, so the next step will be to eliminate one of the variables. So you have here you have another condition which is 2L plus W times pi minus 1/2 is equal to the 500 meter. I'm just wondering whether I have also here. So this is the second step. So the first step is you draw a picture. The second step is to introduce notation. The third step is to express what you want to maximize or minimize in terms of all the quantities. The fourth step is to try to eliminate all the variables such that only one variable is left. And then you just apply what you have learned so far. You can solve this here for L. Then what you get is W is equal to, so 500 minus 2L over, and then you have pi half, so you have here 1000 minus 4L over pi. Now you plug this in here. Okay, so you have A is equal to 1000 L over pi minus 4L square minus 4 over pi L square. No, it's better to solve it for L actually. It doesn't matter. Okay, let's solve. What I wrote actually was L is. It doesn't matter. So we have 250 minus omega pi over 4. So let's plug this in here. So this is the function we want to now maximize. Actually, we have also, as you see here, we have a certain range here for omega. So omega is larger equal than 0 or smaller equal than. Now, the largest value is if L is equal to 0. So you see this will be the case as omega is equal to 1000 over pi. L is equal to 0, right? Our omega is in this range here. Okay, so actually we have to find the maximum here of this function over this range here. So we see that because actually we have then to find out whether what we if we take here just the derivative, we equate it to 0. Okay, then we have to find out whether what we get is actually a maximum. Now, you could argue either by looking at the problem setting. Okay, from the problem setting, you know that what you get will be a maximum. It's kind of clear. Or if you have something like this here, you can actually essentially use the closed interval method. Okay, because you are searching. What you are searching is the absolute maximum of this function here. Okay, over a closed interval. Okay, so the next step is just using the theory we have developed so far. So the derivative will be equal to 250 minus pi over 4 omega. Okay, so you see that this is equal to 0 as omega is equal to 1,000 over pi. Okay, so this is one of the boundary points here. Okay, so in order to figure out whether we have really absolute maximum here or not, we just use the closed interval method. Okay, so we have to evaluate the original function at omega is equal to 0, but this is the absolute minimum, and this here will give the absolute maximum. Okay, so this is already the answer. So for omega is equal to 1,000 over pi, and in this case, the L is equal to 0. Okay, so this means that the maximum is achieved if you choose the two parallel lengths equal to 0, and L is equal to 0. The maximum will be achieved. Now, maybe I should emphasize something here. So as you have seen, okay, normally solving something like this, you do it in several steps. The first step will normally be you plot a picture. Okay. The second step will be you introduce notation. The third step will be you express the quantity you want to maximize or minimize in terms of all other quantities. Then you try to eliminate all the quantities instead of all the quantities but one, because then what you have is the function you want to maximize or minimize is just a function of one variable. And for this situation, we have tools in order to find maximum and minimum. Then normally what you do is you compute the derivative. So you use our tools. Okay, so you compute the derivative, you equate it to 0. But if you just get one solution here, okay, this doesn't necessarily mean you are finished. Okay, so it's not enough just to write your function a as a function of omega, take the derivative, equate it to 0, and say, okay, this must be the absolute maximum. Okay, so you still have to check whether you have really a maximum here. Okay, now because what we are searching for are absolute maximum. So sometimes for some situations it's clear from the situation that there must be an absolute maximum or absolute minimum. So sometimes it's clear from for instance, from a geometric fact that the absolute maximum and absolute minimum exist in this case. Sometimes it's clear that that only the absolute maximum exists. But sometimes it's not so clear. So if you discuss a function, okay, on a closed interval, what you can do is for this situation it's easy to find absolute maximum because we have a method which is called the closed interval method. One of the examples in our textbook is you have given a cylindrical cane which is to be made to hold 1 liter of oil. Now what you are asked is find the dimensions that will minimize the cost of the metal to manufacture the cane. So we draw a picture. Then we introduce notation. So let's say this is our radius here. Call it r, and this is the height here. Now, So what we can do here, we can change R. If we make R smaller and smaller, okay, because you see that because of this assumption here, the volume is fixed, okay. So you see from this assumption here, from this requirement here, that the volume must be equal to 1 cubic decimeter, okay. So you see that the volume is actually fixed. So if you make R smaller, okay, then the height will get larger and larger, okay. And you see that the surface area, okay, of the cane, and this is actually what we have to minimize, okay, will get larger and larger, okay. You see that if as you make R larger and larger, okay, the height will get smaller and smaller, okay, because the volume is fixed, and you again see that the surface area, okay, of the can will tend to infinity, okay. So you will see that because from this already you see that there must exist the absolute maximum for some certain choice of R, okay, because as R tends to 0, the function of the surface area will tend to infinity. As R tends to infinity, it will tend to infinity as well. So there must be some absolute minimum in between, okay. So from this already, here already from the geometric setting, okay, we know that the absolute minimum exists, okay. So if we find then the function and we take the derivative, and the derivative has only one equated to 0 and has only one solution, we know, okay, this must be already the absolute minimum, okay. So we do not have to discuss this point. But if we compute the derivative and we equate it to 0 and we get more solutions, we still have to discuss which one of those solutions is the absolute minimum. So in this case, the volume here is given. So the volume here is R squared times pi times, I'm not sure whether this cane has, because I remember in previous years I have done the same exercise but without a lid. So it actually has a lid. So if we look at the volume, this is something which is given. So this is 1,000 cubic centimeter. Now our function which we want to optimize is the surface area. Okay, so for the surface area we have twice okay, so this is our function which we want to maximize or minimize in this case. So for instance, we express h in terms of r, so we see that h is equal to 1,000 over pi r square. And we plug this into this function here, so we see that s is equal to 2r square pi plus 2,000 over r. So already from this function you see if r tends to infinity, okay, this will tend to, s will tend to infinity, and if r tends to 0 from the right, this function will tend to infinity as well. This is just what I have explained in terms of the geometric setting. Now, the next step is to take the derivative. Okay, so we have 4r times pi minus 2,000 or 4,000 over r square, and we have to equate this to 0. Okay, so this is easy to solve. So we see that r to the cube is equal to 1,000 over pi. So we see that r is equal to the third root of 1,000 over pi. So this choice of r, and you can compute here the corresponding choice of h, will make the surface area of the cane minimal. And as I have explained here from the problem setting, okay, we do not have to discuss whether at this point we really have an absolute minimum, because from the problem setting we already know that an absolute minimum must exist, okay, which is actually between, you can say between r is equal to 0, but you cannot plug this in, so this is for r larger than 0. So somewhere if your r is getting larger, okay, there must at some point there must be attained an absolute minimum, okay, and because we just get 1 0 here of the derivative, this must be the absolute minimum. You can also see this differently. You can say here, if you look at the derivative, if r is smaller than this number here, then the derivative is smaller than 0, so so the function is decreasing, and if r is larger than this point here, then the derivative is larger than 0, so the function is increasing, okay? And now, of course, if you have a point, okay, where to the left the function is always decreasing and to the right the function is always increasing, then there must be, at this point, the function will attain an absolute minimum. This is called, in our textbook, you have a first derivative test for absolute extreme values, okay? And this test essentially tells you what I just said what I just told you. So if you have a point of a given function and the function is to the left of the point is always decreasing and to the right of the point always increasing, then at this point we know already from the original first derivative test that at this point you have a local minimum, but this minimum will not only be local but also global, also absolute. Okay, so this is the absolute, the first derivative test for absolute extreme values. Okay, so maybe here, by looking at this example, I should emphasize one more thing. If you have those two equations, it's not necessary that you use the first equation as I have done here in order to express h in terms of r and then plug this in. It's not really necessary. You can also use the method of implicit differentiation. So you can assume you have done this already, okay? And which means h is a function of r, and then you take the derivative here and here. If you look, because we have to equate this derivative equal to 0, so we have 4 r times pi plus. So, for instance, we assume now that h is a function of r, so we have expressed here already. So if you then look at this, you get 4 times r times pi plus. Then here you have to use the product rule. So 2 times pi times h plus, and for this one you have 2 times r times pi times the derivative of h with respect to r is equal to 0. And you do the same here. So you have 2 times r times pi times h plus r squared times pi times the derivative of h equal to 0. Okay, now you see that, for instance, you can, what is the most easiest? So for instance, you can express the derivative of h here and to plug it in here. So you get, this is equal to minus 2 minus 2 times pi over, no, the pi cancels out. Anyway, minus, divide this, so you have 2 r pi h over minus r times pi square. So this minus 2h over r. Okay, and then you plug it in here. So you plug this in for h, and then you can solve this, for instance, in terms of h, and you will discover that h is equal to 2r, and this is the same answer as we had by using our previous deviation, because so essentially the surface area of this cane is maximized if the h is equal to the diameter of the circle here. Okay, now in our textbook you find many more examples which are related to this topic, optimization problems. We will discuss some more complicated examples next time, because what I have discussed today is more straightforward examples where you can where you immediately know how to set up the problem. But sometimes it's not so obvious, And in some situations, it's even better to introduce. So for instance, you have to maximize some quantity, but sometimes it's better to minimize related quantity or something like this. Something we haven't discussed today is also that sometimes it's in such problems it's possible to simplify the given function. For instance, if the given function contains a square root and you have to maximize it, of course, if you look at the square of the original quantity, if you look at the function which is the square of the original quantity, okay, you do not have the square roots, and this function will be easier normally in many cases to differentiate. But taking the square root will not influence the position at which the maximum or minimum is attained. So sometimes before you go on and compute the derivative, you can simplify the original function. Also, constants normally will not make any difference because here our essentially aim is to find the extreme values. And if our original function is, for instance, 5 times a function, then you do not have to consider the 5, so you can take away constants. This will not change. Of course, it will change the maximum value itself, but it will not change the position of the maximum. So next time we will do some more advanced examples.